Mic is working. See. Start. Good evening, my dear student. Welcome to IMS GATE Academy. Hi, I am Vipin Mishra and I welcome you all in this lecture number 6 of Foundation course on Power Electronics, in which we are going to discuss diode circuit, and through the discussion of diode circuit we will try to understand how to form the waveforms, how the waveforms keep on changing, how to plot the voltage and current if the load keeps on changing. So in power electronics, sometimes you will get RL load, sometimes you will get RC load, sometimes you will get LC load, and you often got confused how to plot the voltage and current waveform patterns across different loads in power electronic converter. Very good evening, Thirumala. So we are going to discuss this topic today. Up till lecture number 5, we have solved some biggest hurdle that were stopping you to become very fluent in the subject power electronics. Like we have discussed how to calculate the energy and power and RMS values of different waveform and across different converter. We have solved one hurdle, how to write the Fourier series expression of different converters. We have also discussed some basics of semiconductor physics and when to use, where to use a particular switch. So all these fundamentals we have discussed. One of the most important thing and one topic in which I have seen students struggling is how to form and how to remember if the load keep on changing, what will be the waveform across different load. Well, you need not to memorize anything, because everything is related to concepts and we are going to cover those concepts in this class. So let me start the topic diode circuit. So through these diode circuits we will try and evaluate what will be the waveform for voltage and current if the load keeps on changing. So first of all, I am going to discuss an RC load. So you can see this circuit in which we are supplying an RC load with some supply Vs and it is connected through a switch and diodes. So when the switch will be on, what will happen? This load and source get connected through switch and diode. So diode get forward bias and the load will the voltage will appear across the load. Now what will be the voltage across capacitor, current across capacitor? So we are going to evaluate all those things and we are going to plot these things, and then we will see how the waveform patterns will be. So just analyze this circuit. So what will happen if suppose the switch gets closed, then what will happen? The source and load get connected, diode will be forward bias, and if we apply KVL, so what will happen at t equals to 0? At t equals to 0, when the switch is closed, then what will happen? The diode is forward biased and the load and source are connected with each other. So at that time, if we are applying KVL, so applying KVL, what you will get? Applying KVL will give you Vs, this is equals to, there might be a current flowing in this circuit like this. So Vs is equals to I into R plus, this is the drop across the resistance and drop across the capacitance will be 1 upon C integral I dt. So this will be the voltage across the resistance and this will be the voltage across the capacitance. Now we have to solve this equation and we have to find out what will be the expression for current in this circuit. So for that we will take the help of Laplace transform. So if I am going to take the Laplace transform here, this equation will modify into, this will become Vs over S, this is equals to R into Is, resistance is independent of frequency and time. So we will get this thing and 1 by C, integration of this will give us Is over S plus Q0 divided by S, where what is Q0? Q0 is the initial charge on the capacitor. So we may also write Q0 to be C Vc0, where what is Vc0? This is the initial voltage across the capacitor. This is the initial voltage across C. Now we have assumed that capacitor is having no initial voltage, so this quantity will be 0, and what we are going to get here is Vs upon S. This will become I of S. We will get R. This will become 0 and we will get R plus 1 by Cs here. Or if I am going to calculate the current Is will be simply Vs upon S divided by R plus 1 by Cs. If we further solve this equation, we are going to get Vs upon R divided by Vs upon R, this will be divided by S plus 1 by Rc. If I am going to solve this equation further, I am going to get this expression. So Is what we have calculated is this much. Now if I am going to take the inverse Laplace transform, then inverse Laplace transform will give me the expression for current, and that expression for current will be It equals to Vs by R e to the power minus T over Rc. So this is going to be the current expression in this circuit if the capacitor is having no initial charge, where I can also write Rc to be tau, or Rc is basically the time constant of this circuit. So what current expression I have obtained? It is equals to Vs upon R e to the power minus T over Rc. So this is what I have obtained here on solving this particular circuit after applying KVL. So current is basically Vs upon R e to the power minus T over Rc. Now the next task that we have to do is to calculate this capacitor voltage. So how we are going to calculate the capacitor voltage? Like the way we have done here. So what will be the capacitor voltage? So let me write the current expression first. So current that we have evaluated is basically Vs upon R e to the power minus T over tau, where what is the value of tau? Tau is the time constant and it is having a value tau equals to Rc. Now if I have to calculate the voltage here, capacitor voltage, then my capacitor voltage will be 1 upon C integral of It dt plus Vc0 if there is any. Vc0 means the initial voltage across the capacitor. So this is the way we will calculate the capacitor voltage. Since we are having no capacitor voltage here, then Vc0 will become 0. Now what we have to do is to put the expression of It that we have just obtained. So It is what? Vs upon R e to the power minus T over tau, or T over Rc we can write, dt plus Vc0 is 0. Now we have to solve this equation. So just integrate this, and what we are going to get? Vs over Rc, I can take it out, and the limits will be 0 to T, because switch has, what we have done here, we have switch on this particular circuit at T equals to 0. So up from 0 to T, we are going to integrate this, this equation, and after integration we are going to get e to the power minus T over Rc upon minus 1 over Rc, and the limits of integrations are 0 and T. Now this Rc and Rc get cancelled, and what we are going to get is minus of Vs. Now we have to put the limits. So we will get e to the power minus T over Rc minus e to the power 0, or ultimately we are going to get Vs 1 minus e to the power minus T over Rc, or T over tau. That is my capacitor voltage. So this is how I have obtained the capacitor voltage and the current in this circuit. So what we have evaluated is, in an RC circuit, the current is basically given by Vs over R e to the power minus T over Rc, and the capacitor voltage that I have obtained is basically Vs 1 minus e to the power minus T over Rc, isn't it? So this is going to be the voltage and current expression across an RC circuit. This is going to be the voltage and current expression across an RC circuit. Now I am going to plot these voltages and current, and then just see what we are going to get here. So if I am going to plot the voltage and current, so now I am going to plot these voltage and current and just see what I am going to get here. So first I am going to plot the voltage and then I will plot the current, or we can plot any one first and then we will plot the next one. So let us consider that I am plotting the voltage first, okay, or let me draw this axis again, because we need one more axis for this current as well. So if this is my voltage, I am plotting one more plot for the current as well. Just a minute guys, let me plot this axis. So now I am going to plot the voltage and current through the expression what I have obtained. So if this is my current I of t and if this is my capacitor voltage V of Ct, then as per the expression, if I am going to plot them at t equals to 0, what I am going to get? At t equals to 0, if I am going to put t equals to 0 in the current expression, I am going to get Vs over R. So at t equals to 0, current is having a magnitude equals to Vs over R. If I am going to put t equals to infinite here, e to the power minus infinite will become 0. So the current finally will become 0. So it will exponentially decrease from Vs by R value to 0, isn't it? So this is the expression of current. Now if I am going to plot the voltage, so if I am going to put t equals to 0 here, this will be e to the power 0, which is 1. So 1 minus 1 will give me 0. So initially the capacitor voltage is 0. Now if suppose I am going to put t equals to infinite here, then I will get e to the power minus infinite, which is 0. So I am going to get a value equals to Vs. So capacitor voltage variation will be like this, starting from 0 and finally it will settle at a value Vs. Finally it is 0 and initially it is 0 and finally it is going to settle at a value Vs, isn't it? Now if you see, have you observed one thing? At t equals to 0, what we are observing here is at t equals to 0, my current is basically Vs over R. And what is my voltage, capacitor voltage? This voltage is equals to 0. So the current is maximum and the voltage is 0, means this is a short circuit condition, isn't it? This is a short circuit. So initially when the switch is at t equals to 0, when the switch is put into the on position, my capacitor is behaving as a short circuit. And finally what is happening? At t equals to infinite, what am I getting is, at t equals to infinite, my current becomes almost 0 and the voltage is exactly equal to the supply voltage. Whatever is the maximum supply voltage, we are getting that across the capacitor. So the current is 0 and the voltage is maximum. Current is 0 and the voltage is maximum. This is a condition of open circuit. So finally, after switching on the circuit, my capacitor finally will become an open circuit. So this concept you might be knowing and I am giving you a proof of these concepts, isn't it? So initially the capacitor will be short circuited when we are going to switch on the circuit, and finally the capacitor is going to be the open circuit, isn't it? So this is what we have obtained here. Okay, so this is what we have obtained here. So initially the current is at maximum and it is decaying exponentially, and finally the current will settle to 0. Voltage is 0 initially, and finally the voltage will be, capacitor will be having exactly the same voltage which we have applied here. Okay, so initially my capacitor was short circuited and finally it will become open circuited. So have you seen how the voltage and current waveforms are varying across an RC circuit? How the current and voltage waveforms are varying across an RC circuit? They are showing some transition and finally they are setting to their final values. So this is how the voltage and currents are varying across an RC circuit. So this was our RC circuit. If I have to summarize this, what we have obtained here. So if I am talking about an RC circuit, then what is going to be the capacitor voltage here? My capacitor voltage is going to be Vs 1 minus e to the power minus t over RC. And what is my current here? My current expression is basically Vs over R e to the power minus t over RC, and this I am getting when I have assumed that capacitor is having no initial charge. So have you seen how we have calculated the voltage and current across the capacitor, and we have plotted them as well, and the behavior of capacitor. Initially it is short circuit and finally it is getting open circuited. Okay, so these expressions that you have obtained and how this circuit is behaving and what is the waveform pattern. So all these things we have discussed. Now, after this, let us consider one condition. Initially, we have assumed that there is no capacitor voltage. Now, in this circuit, if you see, the capacitor is initially charged. Vc0 is not equal to 0, but the capacitor is initially charged to a voltage minus of Vs. So, let us consider that now the capacitor is having initial voltage of minus Vs. So, again, if I am applying the same condition at t equals to 0, if the switch is closed, then the load and source get connected to the diode gets forward bias. If I am going to applying KVL here, what I am going to get? I am going to get that Vs is equals to IR plus 1 upon C again I dt. 1 upon C integral I dt, that will be the KVL here, isn't it? That will be my KVL equation. Again the same concept. If you see, Vs is basically equals to what? The drop across the resistance and the drop across the capacitance. Now if I am again taking the help of Laplace transform to solve this equation, what I am going to get is, I am going to get this will be equals to Vs over S Is into R 1 by C Is over S plus Q0 over S. I have applied the Laplace transform here. Now, as per the last case, we are having no charge across the capacitor, but this is not the case here. We have right now capacitor which is initially charged with the voltage which is equals to how much? Minus of Vs. So, if I am going to put this value here, I am going to get, if I am going to put these values here, I am going to get Is upon S minus Q. I can write C V0, and what is V0? V0 is basically the Vc0 is basically the initial voltage across the capacitor which is minus Vs here. So I am going to get C Vs upon S here. Okay. So this is how we will get this equation. Now we have to solve this equation further, and what we are going to get is Vs upon S. This is equals to Is into R plus, if I multiply this C with inside, I am going to get Is upon Cs minus C and C get cancelled. We are going to get Vs upon S. So this will become twice Vs over S, and I will get Is R plus 1 by Cs. So the same equation we have obtained instead of Vs by S in the last case. Now we have 2 Vs upon S. So if I am going to solve it again for the current Is, initially I will get an expression 2 Vs upon S upon R plus 1 by Cs. So this will be my expression, And if I am going to further solve this, I am going to get it 2 Vs upon R. Then I will be having S plus 1 by RC. So this will be my final equation. Now what I have to do, I have to take the inverse Laplace transform, and after taking inverse Laplace transform, I will get an expression for current IT, which is equals to 2 Vs upon R e to the power minus T over RC. This is what I am going to get here. Isn't it? So if the capacitor was not charged with any voltage, I have obtained a current expression of Vs upon R e to the power minus T over RC. If my capacitor is charged with some voltage of minus V naught Vs, I am having an expression of 2 Vs upon R e to the power minus T over RC. Now in the same manner, I can get the capacitor voltage as well. So what will be my capacitor voltage? So my capacitor voltage I can calculate by using this expression 1 by C 0 to T IT dt plus Vc0, which is the initial voltage. Now just put the values here. 0 to T, what is the expression of IT we have? 2 Vs over R e to the power minus T over RC dt plus the initial voltage that I have here is minus of Vs, isn't it? So this is my capacitor voltage. Now I have to solve this equation only and I will get the desired result. So 2 Vs upon RC it will be. Then I will put e to the power minus T over RC. I have to integrate it, and after integration I am going to get this value 0 to T minus Vs. Now this get cancelled and I have to put the values here. 2 Vs e to the power minus T over RC minus e to the power 0 will be 1 minus Vs. Now I have to resolve this, minus will be here. Now I have to solve this equation further and I am going to get Vct. Vct will be, what values of Vct we are going to get? Minus 2 Vs, that will become plus 2 Vs, minus Vs is Vs, isn't it? Vs minus 2 Vs e to the power minus T over RC. So finally what will be the capacitor voltage? Finally the capacitor voltage is Vs minus Vs 1 minus 2 e to the power minus T over RC. This is going to be the capacitor voltage. So what I have taken here is, if the capacitor is initially charged with some voltage, let us suppose this is minus of Vs, okay? Let me write this in some other way. If capacitor is initially charged with some voltage of minus Vs, what expression we have obtained here is, current expression now has become 2 Vs over R e to the power minus T over RC instead of Vs upon RC, isn't it? This extra factor 2 has come. Now what is my voltage, capacitor voltage? My capacitor voltage has become right now Vs 1 minus 2 e to the power minus T over RC. That is my capacitor voltage. Again Vs 1 minus e to the power minus T over RC we had in the last expression. Again 1 2 is coming here, isn't it? So these are my voltage and current expression across an RC circuit. Now again you can plot these voltages for t equals to 0 and t equals to infinite, and you will get the waveform pattern, isn't it? So what we have analyzed here is an RC circuit. So how the voltage and currents, what will be the voltage and current expression across an RC circuit, that we have calculated, we have plotted, and we have understood the behavior of capacitor initially and finally. Okay, so this is all about the RC circuit. Now let us consider another load, and you are going to see this load very frequently, which is RL load. Most of the loads are of RL type, okay, whether it is motor, whether it is fan, mostly you will get R or RL load to see. Okay, so we have to analyze this RL circuit as well. So we will be doing the same exercise that we have done in RC circuit. So what is that exercise? At t equals to 0, what will happen? At t equals to 0, the switch get closed and the diode get forward biased and the load and source get connected, and if I apply KVL, there might be a current flowing and if I am going to apply KVL, again I am going to get Vs equals to I into R plus L di over dt, which is nothing but the drop across the resistor plus drop across the inductor, isn't it? This is what we have done earlier. Now again we are doing the same exercise. If I am going to apply, if I am again taking the help of Laplace transform to solve this differential equation, I am going to get Vs over S. This is equals to Is into R plus L d by dt of I. That will give me S Is minus IL 0 plus. What is IL 0 plus here? IL 0 plus here is basically the initial value of current here, isn't it? IL 0 plus is the initial value of current. So this is the initial current across the L. Initial current across L. So since I have assumed that there is no initial current here, so I will assume that IL is 0. So no initial current or no initial condition. So no initial condition means my IL 0 plus will be equals to 0. So I am going to get Vs over S. This is equals to R plus SL into Is. Or I can write Is to be equals to Vs over S upon R plus SL, or I can modify this equation and this will become Vs over L upon S, S plus R by L. Or I can further solve this equation after partial fraction. This will become Vs over R upon S minus Vs over R upon S plus R by L. So this is what I am going to get if I further solve these steps, okay. So Is we have obtained like this. Now if I am going to take the help of inverse Laplace, my current It will become Vs over R 1 by S. The inverse Laplace will be 1 only, and Vs over R. Here I am going to get e to the power minus t upon tau, where I am considering tau to be L by R. So this is going to be my current expression here, okay. So again, if you see the same way what we have done in case of RC load, we are applying the same steps here and we have calculated the current expression, okay. So what current expression I am getting here? The current expression that I have obtained is basically I of t. This is equals to Vs over R 1 minus e to the power minus t over tau, where tau is the time constant having a value L by R. Tau is the time constant having a value L by R. So this is what we have obtained here, the expression for current. Now what will be the inductor voltage? So if I am going to calculate the inductor voltage right now, VLT, this will be equals to L di over dt. So I expression I have already calculated. I have to differentiate this expression. So I am going to put the value of I here, which is this much, okay. Now what I have to do is to integrate this particular, I have to differentiate it. So on differentiate, and what I am going to get, this is going to give me 0 minus e to the power minus t over tau minus 1 over tau. Again this will be equals to LVS upon R. Minus and minus get cancelled. 1 upon tau will become what? R by L. So I am going to get R by L e to the power minus t over tau. Now this get cancelled, and finally what I am going to get as expression for inductor voltage is equals to what? Vs e to the power minus t over tau, isn't it? So this is going to be my expression for voltage, and this was my expression for current. So let me write them again. So what expression I have obtained? The current, the inductor voltage is given by this expression, which is equals to Vs e to the power minus t over tau, and the inductor current or the circuit current basically, because they are connected in series. So the circuit current is I of t, which is equals to what? which is equals to Vs over R 1 minus e to the power minus t over tau, where what is tau? Tau is the circuit time constant, which is L by R. So these expression for voltage and current we have obtained in case of an RL load. Now if I am going to plot these again, just see what I am going to get here. So first I will plot the current and then I am going to plot the voltage. So if suppose I am plotting the current first, so if this is my current IT and if this is my inductor voltage VLT. So if I am going to put the value of t equals to 0 in this expression, so if I am going to put t equals to 0 here, I am going to get a voltage of Vs. So initially the capacitor inductor voltage is Vs, and finally what is going to happen? Finally, if you see, if I am going to put t equals to infinite, this voltage will decay exponentially and finally the value of voltage will be 0, isn't it? Similarly, if I am going to plot the current, so if I am going to put t equals to 0 here, what will be the value of current? So the value of current I am going to get is 0, and finally I am going to get Vs by R. So the current expression will be like this. Finally the current will settle up to a value of Vs by R, and initially the current is 0. Now if you analyze these circuit or if you analyze these waveform, can you see what we have obtained here? So if I am talking about at t equals to 0, so at t equals to 0, what is the scenario? At t equals to 0, the current is 0 while the voltage across the inductor is having the maximum value. That means current 0, voltage maximum. Current 0, voltage maximum is an open circuit condition, isn't it? This is an open circuit condition. Similarly, if I am going to apply t equals to infinite, means as the time progress, this is the initial conditions, this is the during the transient. If suppose I am switching on the circuit, what is happening? During the switching on, the inductor is behaving as an open circuit. As the time progresses, means as the time reaches to a certain value, you can see the current is settling up to a value Vs by R, and the voltage across the inductor is 0, means finally it is getting short circuit. This is what you know, but you have seen the proof for that particular thing, isn't it? So if I compare this RL circuit with RC circuit, when it comes to the capacitance, it was initially short circuited, finally getting open circuited. When it comes to the inductive circuit, RL circuit, initially it is open circuit and finally it is setting up to a short circuit, isn't it? So this is how inductive and capacitive circuits are going to behave. So these are the expression for current across inductor and voltage, isn't it? So if I have to summarize again, so what values of voltage and current I have obtained here, you can pretty easily memorize these values, or you can pretty easily remember these values. So what is the expression of voltage? The expression for voltage is Vs e to the power minus t over tau. And what is the expression for current? Current is Vs over R 1 minus e to the power minus t over tau, where what is tau? Tau is basically L by R, the time constant of the circuit. And initially my inductor is open circuited, finally it is getting short circuited, isn't it? This is what we have analyzed here. Okay. Now let me ask you one thing, and that is a special case that you will see generally in power electronics. Okay. What if suppose I am opening the switch, then what will happen? If suppose I am opening this switch, so if the switch gets open, let us consider I am opening the switch. Okay. So what is the expression of my current here? my current expression is, what is the expression of current that we have obtained? Vs upon R1 minus e to the power t upon tau. So this current is flowing in the circuit. If suppose I am opening the switch right now, so if I am opening the switch right now, that means there is no connection of load with the source. Vs will become 0. In this circuit, no source voltage is applied. So IT, current, might have become equals to 0, isn't it? So what am I trying to say is, let the switch is open. So if the switch is open, what will happen? If the switch is open, the current will become 0, isn't it? But we have inductance here. We have inductance here, and as per the inductance properties that you might be knowing, that it will not allow the sudden change in current, isn't it? The current across the inductance cannot change suddenly. But if suppose I am opening the switch, then the current is forced to become 0 because there is no more supply available here. So the current is forced to become 0, but you know that across an inductance, current cannot change instantly. So this inductance will not allow this particular change of current. Okay. So what am I have to write? But current across L can't change suddenly, isn't it? Can't change suddenly because this is unnatural. This is not practically possible. So we have to do some arrangement. Yes or no? If suppose the switch get open accidentally, or suppose if we are opening this, we can't open this practically. This is not correct thing to do. So if suppose switch get open accidentally, then what will happen? The current will become 0 because there is no more source available. But if this is so, this is a violation, isn't it? Violation of rules. We can, current across the inductance cannot change instantly. So we have to provide some meaning, and that purpose we have solved through providing this extra diode in parallel to the load. This extra diode in parallel to the load. Okay. How this is going to solve the purpose? Let us suppose now the switch gets open. Okay. So if switch gets open, let us suppose the switch is closed. First of all, let us suppose the switch is closed. So if switch is closed, then what will happen? So if switch is closed, then the current is following this path. Okay. And what is the polarity of inductor then? Inductor voltage might be having this polarity. So this is the beginning polarity of inductor. Now due to this polarity of inductor, this freewheeling diode is reverse bias. This is not at all working. Now if suppose when the switch is closed, then diode is on. Okay. If suppose the switch is open, if switch gets opened, then what will happen? So if the switch gets opened, the current is forced to become 0, but the current across the inductor cannot change suddenly. So in order to oppose this change, the inductor will reverse its polarity. In order to just oppose this change, the inductor will reverse its polarity. So if the switch gets opened, there is no source available. So it is impossible to sustain the current by the inductor. So inductor will oppose this to happen. So it will change its polarity, and due to this change of polarity, now freewheeling diode will come into play. So freewheeling diode will get on. This diode is called freewheeling diode because when the switch was on, inductor is storing energy. Now when the switch is off, then inductor will release its energy through freewheeling diode into this resistance. So that is the purpose. That is the why it is called as freewheeling diode. Now it is providing a path for inductor energy to release. So you can see here, if the switch is open, then freewheeling diode will come into play, and that problem, if switch gets open, the current might have become 0, and inductor will not allow this sudden change of current. So how inductor has opposed that? Inductor has reversed its polarity, and as we have freewheeling diode, so the current will circulate in this path and in this way. So current has suddenly not become equal to 0. So inductor have stored energy when switch was on, diode was forward bias. Now it has got a path to release its energy through this freewheeling diode into the resistance. So now we have solved this problem, isn't it? So this is why the freewheeling diode is very, very important. So when the switch is on, we will be having this circuit. When the switch is off, then this particular circuit will come into play. Okay, now we have to analyze this circuit. So what will be the initial current across this circuit? Can you see here? These graphs that we have plotted here. So if the switch is on, the current will finally settle to a value Vs by R. Now what we are doing, we are switching this particular, we are switching off this, just turning off this switch. So at what value we have left the current to be Vs by R. So initially when this circuit will start working, the current might be having a value equals to Vs by R. And since when freewheeling diode will be on, there will be a direct short circuit across the load. So V0 will be 0. So these are the initial condition for this circuit. Now if I am applying KVL in this circuit, then what I am going to get? I am going to get, if the current in this circuit is I, then I am going to get I into R plus L di by dt. This is equals to 0. As the freewheeling diode will on, this load will get short circuit. So this V0 will be 0. So on applying KVL, IR plus L di by dt will be equals to 0. Again, if I take the help of Laplace transform, then this will become Is into R plus L S into Is and minus IL0 plus. So can you now tell me what is the value of IL0 plus? Now in this circuit we have some initial value of current to analyze this circuit, and that value is Vs by R. So we are having this value here available equals to 0. So ultimately what I am going to get is VSL by R. This will be equals to, if I take Is to be common, I am going to get R plus SL here. So what will be the current expression? Current expression will become VSL by R. L and L get cancelled and I will get Vs over R upon S plus R by L. This is what I have as current. So this is my value of current here. So now if I am going to take the inverse Laplace transform, my current will be Vs upon R e to the power minus T over tau, where tau is basically L by R. So this is my current expression for this particular part of circuit, isn't it? This is going to be my current expression for this particular part of circuit. Now if you see where we have left, if you see where we have left in this circuit, so where we have left in this circuit, if you see I am getting this current expression. So what I am having here is, if suppose, let me draw the waveform and then you will be able to understand. So right now what stage we have reached is, so if I am going to plot the current right now, just see what is happening here. If I am going to plot the inductor current right now, so earlier when the switch was on, the waveform for current was, it is starting from 0 and it is establishing up till the value, it is establishing a value of Vs by R, isn't it? This is what we have obtained when the switch was on, means when the diode is on. This part of waveform we have obtained when the diode is on. Let me mark a boundary here. So this is going to be the boundary here. Now let us suppose at this moment we have just opened that switch, then this freewheeling diode will come into play. And what is the expression we have obtained for this particular circuit? So for this particular circuit we have obtained an expression of Vs by R e to the power minus T by tau again. So this is going to be the moment where the freewheeling diode will start acting. Yes or no? This is going to be the moment where the freewheeling diode is going to start Now at this moment freewheeling diode is having a value equals to Vs by R, isn't it? This is a t equals to 0 moment for this freewheeling diode. So at this moment it is having an initial value of Vs by R. If you see, initial value it is having is Vs by R. And at what value it is going to settle? Initial value is Vs by R, and it will start decreasing exponentially, and finally it will be setting up to a value equals to 0. As t approaches infinity, what we are going to get? So as t approaches infinity, we are going to have a value of current equals to what? Equals to 0. So can you see here? If freewheeling diode is conducting, we are going to have this particular part as well. So this is the moment when the diode is on, inductor has stored energy, current has reached from 0 to maximum. When freewheeling diode is on, inductor is releasing energy, current has reached from maximum to 0. So this is going to be how the RL circuit is going to behave. Now this particular current behavior you are going to see again and again and again across all types of converter, because mostly we have to analyze this particular type of load. Let me draw it more clearly, because this is a very important part. So what we have obtained here is, this is how my current is going to behave, isn't it? Are you able to see this change? This is how my current is going to behave. When the freewheeling diode, when the diode is on, so the current has settled up to a value Vs by R, and when freewheeling diode will come into play, it is reducing from Vs by R to 0, isn't it? So this type of pattern, this type of waveform behavior, we are going to plot again and again in power electronics. RL circuits are very important to analyze. So what is the purpose of this freewheeling diode? So if we are using RL load, it becomes essential to use freewheeling diode unless we have something else in the circuit present, isn't it? Because remember one fact, current across the inductor cannot change instantly, isn't it? So this is going to be the pattern that you are going to see across rectifiers, across choppers, and very specifically you are going to see this pattern of waveform in inverters. So now you must have got how this is coming. Okay, now what type of if we just reduce into it this particular waveform into its smaller version, what waveform you are going to see more and more in power electronics is this kind of waveform. Not this specifically, you are going to see this kind of waveform more and more in power electronics. See, this kind of waveform you must have seen. So how this is coming? This is coming just because of these factors what we have analyzed here, isn't it? So current across an RL circuit first reach up to a maximum value, and then when the freewheeling action will be there, it will be coming back from that maximum portion to 0 portion. Okay, so this is very important. You are going to see all these patterns very frequently in inverters, rectifiers, choppers, everywhere. Okay, so we have understood how the RL circuit is behaving and what is the behavior of this freewheeling diode is. Now another important circuit is LC circuit. Whenever we want to turn off the switch, this circuit becomes more important. These can be the part of load commutation as well in case of the SCRs. Okay, so LC circuit we have. So again we will be applying the same steps. So at t equals to 0, what will happen at t equals to 0? We will switch on this particular switch and the diode gets forward bias, and then if we apply the KVL, there might be a current flowing, and then we apply the KVL, Vs will be equals to L di by dt plus 1 upon C integral of I dt, which is nothing but VL plus Vc. Now we have to solve this equation, and how we are solving this equation? By applying Laplace transform. So if we take the Laplace transform of this wave, we are going to get S of L. Since right now you can see there are no initial condition in this circuit, so I can just move into the very next step. If there are no initial condition in this circuit, we are going to get S into L IS plus IS upon CS, isn't it? This we have seen in RL and RC circuit, so I can apply this condition directly because there are no inductor current, initial inductor value of current, and there is no inductor voltage, capacitor voltage as well. So we can directly write this equation right now. We have practiced that much. So they are going to get SL plus 1 by SC here. Now what will be the value of IS? So this is going to be VS upon S, SL plus 1 upon SC. This is what we are going to have here. Further solve these and we are going to get S square LC plus 1 upon SC, which will reduce to CVS upon, we can take this LC out from here, and then this will become S square plus 1 upon LC. So this is my expression for IS. So up till where we have reduced this equation, IS is basically C and C get cancelled. So we have got VS over L divided by S square plus 1 by LC. So up till that moment we have obtained this equation. I hope you are having no hesitation as per the solution of these equation, and you have developed an approach of analysis of these loads, and whenever you have to find the voltage and current expression, very easily you will be able to do that thing, isn't it? If suppose there are some little changes in the circuit, you will be able to apply those as well. And what are those small changes? Application of having some initial condition as well, isn't it? Now we have to solve this further. So what we have obtained here is I of S. This is basically Vs over L upon S square plus 1 upon LC. Let me write omega equals to 1 upon under root LC. If I am writing this, I can modify this particular equation into Vs upon L S square plus omega naught square, and after that let me multiply with omega naught and divide by omega naught as well. So what I am going to get? I am going to get Vs upon omega naught into L, and inside the bracket I am having omega naught upon S square plus omega naught square. So what is going to be the value of Vs into omega upon omega naught L? What is omega naught? Upon 1 upon under root LC, and this is L. So what we can write it? We can write it Vs under root C by L. Is this correct? So we can write this expression to be Vs under root C by L. Yes or no? So I am replacing this expression with this quantity only, which is Vs under root C by L omega naught upon S square plus omega naught square. And if I am going to take the inverse Laplace transform, IT will be Vs under root C by L sine of omega naught t. You know this is what? This is the Laplace transform of sine omega t. So this particular expression I have obtained for current in this circuit. Okay. So this particular expression I have obtained for current in this circuit. Is that clear? Is that clear? I suppose that you are not having any problem in calculation of this. Let me clear this right now. So this expression of current we have obtained here. Okay, let me write this omega naught, which is 1 upon under root LC. So this particular expression we have obtained. So my current right now in this circuit is, let me write Vs under root C by L to be IP. Okay, IP, that is the peak value sine omega naught t, and you know that this is also equals to Vs under root C by L sine omega naught t. Now I'll recommend you to memorize this particular expression, because in across pure power electronics you are going to encounter this expression again and again. Okay, so just remember this expression. Now IT we have obtained. What will be the inductor voltage? So inductor voltage will be L dit over dt. So just put the values here. L d by dt of Vs under root C by L sine omega naught t. Okay, and just solve this particular expression, and you are going to get the value of VLT as Vs cos omega naught t. I can very easily calculate from this expression, isn't it? So without solving, I know that this is going to be the value of VLT. So this is my inductor voltage. This is my current of this circuit. Now if I have to obtain the capacitor voltage, so can you see here, what is the capacitor voltage? Capacitor voltage is simply Vs minus VL. So we are going to apply this condition and we will get the value of capacitor voltage. So this is going to be Vs minus VL. Vs minus, what is VL? VL is Vs cos omega naught t. So this is my capacitor voltage, or I can write this that capacitor voltage is Vs 1 minus cos omega naught t. So this is my capacitor voltage. In current across the circuit, voltage, inductor voltage and capacitor current, all that things we have calculated, and I don't think there is any hesitation you might be having regarding the calculation of these quantities, isn't it? I don't think so that you are having any hesitation in order to calculate these quantities. Okay. Now if suppose I have to plot these values, so what value of current I have obtained? Current value that I have obtained is IP sin omega naught t. The inductor voltage that I have obtained is Vs cos omega naught t, and the capacitor voltage is basically Vs 1 minus cos omega naught t. This is what we have obtained. Let us plot all these quantities here. So if I am going to plot IT, IT is basically following the sine curve. So as per the sine curve means it is following the sine curve, and when we will reach up to this point, which is what, if we are going to reach up till this point, which is what, omega t equals to pi point. So at this point you can see the current will become 0. So this is the peak value of current, that is IP, and at pi the current has become 0. So once the current will become 0, that means diode must have turned off, isn't it? Once the current has become 0, that means the diode must have turned off, yes or no? So the diode has turned off right now because the current has reached a value equals to 0. So current has become IT has become 0 at omega t equals to pi. So if I am going to ask for what duration the diode is conducting, so the diode conducts for a duration t equals to pi by omega naught, or I can say pi under root LC. So this is a very, very important expression as far as the gate questions are concerned. Okay. So it is following sine curve, and you see at pi this has automatic current has become 0. So from there onward the diode will turn off and the current has become 0. Now how the inductor voltage is varying? It is following basically the cosine curve. So when we will reach up till the moment pi by 2, the voltage will become 0, and at the moment pi the voltage will become negative. So it is plus Vs and this is minus Vs. So when we have reached pi moment, current has become 0, and at that moment the inductor voltage will also become 0, because ultimately the inductor voltage is L di by dt. If there is no change in current, means if there is no current, how can the inductor voltage will be there? So this is how the inductor voltage is varying. So initially you can see it is positive, finally it is negative. So from 0 to pi by 2, inductor might be storing the energy, and from pi by 2 to pi, inductor is releasing its energy, and that's why its voltage is negative. Now when it comes to plotting the capacitor voltage, if I put omega t equals to 0 in this capacitor expression, in this capacitor voltage expression, if I am going to put omega t equals to 0, cos 0 is 1, 1 minus 1 is 0. So I am going to get a 0 here. If I am going to put pi by 2 here, cos pi by 2 is 0. So I am going to have Vs. So at pi by 2, the capacitor voltage reaches up to a value Vs. If I am going to put omega t equals to pi, that will be cos pi, which is minus 1. Minus and minus get plus, we will get a voltage equals to 2 Vs. So from 0 to Vs, and then finally it is reaching up to a magnitude of 2 Vs. So this is what this is. At this height, the voltage will be Vs, and at this height, the voltage will be basically 2 Vs. Now from here onward, it will remain on this voltage 2 Vs, because right now the capacitor voltage is not changing, no current is there, isn't it? So can you see here, once the diode is conducting up till this moment, isn't it? This is the moment where the diode was on, and this is the moment from where the diode is off. So when the diode is off, if I am asking when the diode is off, when diode is off, what is the capacitor voltage? So when the diode is off, the capacitor voltage is basically 2 Vs. What is the inductor voltage? This is basically equal to 0. And for what duration the diode conducts is pi under root LC. So simply by looking into these three equations, anywhere, anytime you can analyze all these concepts, isn't it? So do we need to switch off the circuit in order to turn off the diode? I don't think so, isn't it? Because you can see, after turning out at t equals to 0, and after this particular time pi under root LC, the diode has self commutated, means diode is self off, isn't it? We haven't applied, we haven't switch off the circuit, we haven't turned off the switch, and the diode is getting off just because of this capacitor, which is charged with a voltage of 2 Vs. So imagine a situation when the capacitor will get charged in this circuit for voltage 2 Vs, then the negative side might be having 2 Vs, positive side might be having Vs, means the diode gets reverse bias. So this type of turning off is called as load commutation. This type of turning off of the circuit is called load commutation. So if I have to summarize what I have obtained across this circuit is, so what is the expression for current here? The expression for current is Ip sine omega naught t, and you know the value of Ip, which is equals to Vs under root C by L. What is the expression for voltage across inductor? This is following the cos curve. What is the expression for capacitor voltage? This is equals to Vs 1 minus cos omega naught t, and diode is self commutating, diode is turning off automatically. Diode conducts for a time which is equals to pi under root LC. So after that time, this particular time, the capacitor is charged to a voltage 2 Vs, so the negative side is getting 2 Vs, positive side is only having Vs, so this diode gets turned off, it gets reverse bias, and it is turning off automatically. We are not forced to just turn off the switch and the diode is getting off. Okay, so this type of situation, in this particular situation, these circuit are also called as the load commutation circuit. Okay, we can also call them load commutation circuit, where the load element are supporting us in turning off the switch as well, isn't it? So load commutation circuit we can also call them. Now let me consider one special case. Let us suppose initially we have assumed there is no initial voltage across the capacitor. Now in this circuit, if you see, let us consider that the capacitor is having a voltage Vc equals to V0, isn't it? There might be two cases possible. In case 1, let us suppose that the capacitor is having a voltage equals to V0. Okay, when capacitor voltage is 0, then what is the current and voltage we have? If suppose capacitor voltage is 0, means initial capacitor voltage is 0, Vc 0 A plus A is 0. In that case, what are the values of current and voltage we have? This is given by, let me write here, at Vc 0 plus equals to 0. The current expression that we have is Ip, or let me write the full expression. which is Vs under root C by L sin omega naught t. What is the voltage across inductor? Vs cos omega naught t, isn't it? And the capacitor voltage, I don't mind that voltage, because anytime you can calculate this voltage by Vs minus Vl. Anytime you can calculate the capacitor voltage. So let us consider the first case in which the capacitor is charged with plus V0 voltage. So what you have to do? You have to do the same exercise. You have to solve all those things. Now you will be putting some initial values of voltage here, and then finally you will be getting an expression. But you don't have to do again and again the same exercise. Let me tell you what is going to be the expression. If the capacitor is charged with some positive voltage, just see how the expressions are going to change. IT will become Vs minus V0 under root C by L sin omega naught t. Capacitor inductor voltage will become Vs minus V0 cos omega naught t, and you can calculate the capacitor voltage just by doing this exercise, Vs minus Vl. So if the capacitor is charged with positive voltage, instead of Vs you will write Vs minus V0. Now we have a case 2 as well. So in case 2, let us consider if the capacitor is charged with some negative voltage. So if the capacitor is charged with some negative voltage, I am sure you are able to predict right now what are going to be the expression. This will become Vs plus V0 under root C by L sin omega naught t. And what will be the inductor voltage? That will also be Vs plus V0 cos omega naught t, isn't it? Anywhere, anytime you can calculate these voltage, you can write these expression. Okay, if we are having capacitor voltage charged with positive voltage, so instead of Vs I will write in all these expression Vs minus V0. Okay, capacitor voltage expression you don't have to remember, just remember IT and VL. Vc capacitor voltage you can calculate any time by just doing Vs minus Vl. If my capacitor is charged with negative voltage, Vs plus V0 I will be writing everywhere, isn't it? This small exercise you have to do, and you will get the results for this particular case. Okay, you are going to get results for these particular cases. Now again one special case. Here you can see supply is available. Let us consider a case where supply is not available. Supply is not available means here we have the Vs value equal to 0. And just by looking into the capacitor, can you tell me what is going to be the Vc value? Initial capacitor voltage is negative here. Initial capacitor voltage is negative here. So which case you are going to apply? Initial capacitor voltage is negative here, so you are going to apply this particular case, but Vs you have to put 0. So what expressions you are going to get? IT expression will be equals to V0 under root C by L sin omega naught t, and the inductor voltage expression will be V0 under root V0 cos omega naught t, isn't it? Just see this case. Vs we have to put 0, and what is the value of V0? V0 is V0. We have to put this case because Vc is negative here. So Vc is having initial voltage which is negative here, and almost one more case we have, that is Vs is equals to 0. So how the expressions are going to be modified? Vs is not there, so Vs we will put 0, and this is the case where Vc is having negative voltage. So this is how our expressions are going to be modified. Yes or no? So these are the loads that you will see very normally in power electronics. So how they are changing, what is happening, you can analyze all those things very easily here. Okay. Now let us solve some questions, and then we will see. You can see there are gate questions asked from the particular topic as well. So what has been asked in this question is, it has been said that in the circuit of figure the switch S is closed at t equals to 0. So at t equals to 0 we are closing the switch with VL 0, VC 0, no initial condition. Okay. In the steady state the voltage VC is equals to, this is case number, this is a normal case, no inductor voltage. Okay, no inductor voltage, let me write L here, this is not R. So no inductor voltage, this is not R, this is L. LC circuit is there, no initial inductor voltage, no initial capacitor voltage, and they are asking at the steady state, what is going to be the capacitor voltage? So at the end, what is going to be the capacitor voltage? What is going to be the capacitor voltage? So inductor voltage, if I talk about, this is following cos curve, and capacitor voltage, if I talk about, this was Vs1 minus cos omega naught t. So if you could have remember, we have plotted the Vc curve and it was like this. The capacitor voltage at the end was 2 Vs. So Vs is basically 100, 200 will be the answer, isn't it? This we have covered in the class. Now most of the students must have written Vs only. They just thought final condition we are talking about. Finally the inductor will become short circuit. This Vs will appear at this capacitor. So answer is Vs, not Vs. It is 2 Vs. And how this is 2 Vs? You can just see in these waveforms. We have plotted these cases. Can you see here? And finally, what is the capacitor voltage? Finally, the capacitor voltage is 2 Vs. Finally, the inductor voltage is 0. Finally, the current is 0. Okay, not Vs, 2 Vs. So just remember this fact, and you can get a problem to be done here. Now just see this particular circuit, GATE 2010 problem. In LC circuit shown in the figure has an inductance L and capacitance C given. Initial current through the inductor is 0, no initial current across inductor, and in our case as well we haven't considered any initial current across inductor, while the initial capacitor voltage is 100 volt. So as per the polarity you can see initial capacitor voltage we are writing it Vc naught, which is V naught here, and as per the polarity this is Vc naught is what? Can you see just third case of us, this particular case where Vs is 0 and capacitor is charged with negative voltage. Isn't it the similar case that we have in this case? So Vc is basically what? Vc is basically here is minus of V naught, isn't it? So what we have to calculate, what is the current here? So can you just tell me the current expression? When Vs is equals to 0 and Vc is minus V naught, if you could have remember, if Vc capacitor initial voltage is plus V naught, we are writing Vs minus V naught everywhere. When capacitor voltage is minus V naught, we are writing Vs plus V naught everywhere. But here the capacitor voltage is negative, so we have to write Vs plus V naught, and Vs is 0. So expression will be V naught under root C by L sine omega naught t, isn't it? So what is V naught? V naught is given us, which is what? 100 volt. Okay, this is the initial voltage which is given 100 volt. But looking into the polarity, we will get the value, it is positive or negative. Okay, now under root C, C value is 10 microfarad, and what is the value of L? L value is 1 millihenry. Sine of omega is basically what? What is value of omega naught? Omega naught is 1 upon under root LC. So just put under root LC. L is 1 into 10 to the power minus 3. C is 10 into 10 to the power minus 6 into T here. And after finally solving, you are going to get 10 sine 10 to the power 4t. So this is how you can solve the gate question in one step only. Okay, so whatever we have covered in the class, exactly the same concept we are utilizing here in order to solve these circuits. Yes or no? So I hope you have got this question right. This is 10 sine 10 to the power 4t, which is correct. Now see this particular case. Okay, so in the circuit of adjacent figure, the diode connects the AC source to a pure inductor. So whatever we have done is for DC. What if the source changes to AC and we have here pure inductance, R is also not there? What we have to do? Analysis remains the same. Whatever we have done, we will be doing the same thing here as well. What we have to find? The diode conducts for. So for what duration the diode will be conducting, we have to determine that. So this is AC source. So if this is AC source, so Vt will be Vm sine omega t, isn't it? If I apply KVL here, if the diode is on, let's consider the diode is on. So if you are applying KVL here, then this VT voltage will be equals to VL voltage, isn't it? If this is my VL voltage, then this VT is equals to VL voltage. What is VT? VT is Vm sin omega t, and how do we write VL? VL is L di by dt. Okay, let me consider a current here. Now if I have to write di, I can write it Vm by L sin omega t dt, isn't it? Earlier also when DC source was there, we have applied KVL and then we need to take the Laplace transform. Do we need to take a Laplace transform here? Isn't it? We don't have to take, because this can be easily solved. So di, let me consider that the current is changing from 0 to I naught. Okay, what I have considered here is the current is changing from 0 to I naught. Is that clear? I have considered that the current is changing from 0 to I naught, and what I have to do, I have to integrate this particular factor here. So if I am going to integrate it, I am going to get I naught here, and this will be Vm by L sin omega naught t. This will be give me cos omega naught t minus cos omega naught t, isn't it, by omega. This is going to give me this value minus cos omega t upon omega. This is what I am going to get, and let me consider we are getting a constant as well. This is the way we will solve the integral. So I am going to get Vm by omega L minus cos omega t plus k here. This is my expression. So let me write this expression. I naught is basically minus Vm by omega L cos omega t plus k. This is what we have obtained. So at omega t equals to 0, just we have started analyzing the circuit, then there will not be any current, isn't it? So if I am putting this value here, so this will be Vm by omega L cos 0 will be 1 plus k. So my k value will be Vm by omega L. Let me call this equation 1. So if I am going to put this equation, this value in equation 1, so from equation 1, what I am going to get? I naught expression. If I put the k value, I am going to get Vm by omega L 1 minus cos omega t, isn't it? This is what I have obtained. Now let me plot this and I will get an idea for what values of omega, or I will get an idea for what values this particular diode will be on and for what values it will be off. Okay, so I'll get an idea regarding that. So let me just evaluate these things. So if suppose this is my current I naught omega t, if I am going to put omega t equals to 0 here, then what will happen? If I am going to put omega t equals to 0, I am going to get cos 0, which is 1, 1 minus 1 is 0. So this will be equals to 0 at omega t equals to 0. If I am going to put omega t equals to pi, then what will happen? This will become cos of pi. Cos of pi is minus 1. Then this will become 2 Vm by omega L, isn't it? And if I am going to put omega t equals to 2 pi, cos 2 pi is again what? Cos 2 pi or cos 0. They are having same value, which is 1. So 1 minus 1 will be 0. So if I am going to plot this, what I am going to get is this shape, and at 2 pi and 0, this is having a value 0, and at pi this is having a value equals to what? This is having a value equals to Vm by omega L, 2 Vm by omega L, which is the maximum value of it, isn't it? 2 Vm by omega L, which is the maximum value of this particular, which will be the maximum value. If we put omega t equals to pi, cos pi is minus 1, so we are getting 2 Vm by omega L, which is going to be the maximum value. Okay, let me write this here because I have to tell you some other concepts as well. So my maximum value is 2 Vm by omega L. Okay, so when it comes to the L load, this waveform I have drawn for L load, pure inductive load. So you can see current has started building from here. It is changing as per this expression, which is very important for you. It is changing as per this expression, and you can see at 2 pi this is again becoming equals to 0. So current has again become equals to 0 at 2 pi. That means the diode will stop conducting from here, isn't it? So what movement the diode has conduct? For 2 pi, that means diode has conduct for 360 degree. Okay, so if it is a pure inductive load, the diode or switch will conduct for what duration? 2 pi. If suppose this is a pure resistive circuit, then diode would have conducted only for pi. Okay, if this is a pure resistive circuit, then diode could have conducted only for phi. And if it is an RL circuit, then diode could have conducted in between this pi and 2 pi. Okay, so this would have been the waveform for RL load. Okay, these analysis are very important, becomes very important for you if suppose you are dealing with the rectifiers. Okay, so if it is an L load, diode will conduct for the switch. Forget diode, switch will conduct for complete 360 duration. If it is the resistive load, diode could have conducted only for pi duration, 180 duration, 1/2 cycle, okay, of AC voltage. Is it clear? Just a second. So if it is an RL load, diode could have conducted in between pi and 2 pi, isn't it? So this is how you can analyze these circuit. What will be the shape of current in RL case? You very well know this, isn't it? This could be the shape of current in case of an RL load, isn't it? So this is how you can analyze these things. So we have got the answer. The diode will be conducting for what duration? It will be conducting for 360 duration. What if we have replaced the diode with the capacitor and we have changed this question? This is not a gate question, but this can be a gate question. So the same circuit we have, but the inductor is now being replaced with the capacitor. So if suppose we have capacitor being supplied by AC circuit, so this is the situation that we are in. Right now we have the capacitive load. In that case, the capacitance, diode will conduct for what duration? So again, if I have to calculate the capacitor current, how I am going to calculate the capacitor current? Capacitor current is simply I naught is C dV naught by dt. And you know that when diode will be on, if suppose this is my capacitor voltage, okay, let me write here Vc instead of V naught, let me write here Vct. Okay, so when diode will be on, I will be having my input voltage exactly equals to the capacitor voltage. So what I can write in place of capacitor voltage is C d by dt of Vm sin omega t. Now if I integrate it, I am going to get Vm C omega cos omega t. This is going to be the expression for current. If I am going to plot this current, this is following the cos curve, isn't it? Having the maximum value of Vm C omega. So this is having maximum value of Vm into C into omega. And as soon as I will reach at pi by 2, you can see the current has become 0. And from there onward, it will remain 0. So if I am going to ask you for what duration the diode will be conducting, if we have capacitor load, it will be conducting only for 90 degree. And that is why we will never allow pure capacitive load. What is the purpose of having pure capacitive load? The current has become immediately 0 after pi by 2. Voltage could have become immediately equals to pi, isn't it? Voltage might be rising from 0 and it has reached a value of pi. So this will be your voltage. It will remain at Vm. This is the voltage and this is the current. So can you see current has become 0 after pi by 2. Voltage has established itself on the value Vm. So is there any purpose of using this capacitive load? And that is why pure capacitive load you will never see anywhere. The load that you will see is this particular kind of load. R load, L load or RL load, isn't it? R load, L load or RL load. If suppose this is an R load, then what will happen? Half cycle current might be flowing. For the next half cycle, switch will be off, current might not be flowing. If this is pure L load, then what will happen? From 0 to pi, the energy will be transferred from load, source to load, and for the next pi to 2 pi, energy might be returning to the source. If it is an RL load, same thing will be done, but the duration will be less. Okay. For up till the moment pi, source will be transferring power to the load, and from pi to whatever is the moment, okay, this moment, load might be transferring power to the source. So this is all about this lecture. We have covered some important loads and how the current and voltage are varying. If suppose the nature of supply is DC, if suppose the nature of supply is AC, if suppose the load is L, C, R, or if suppose the load is RL, LC, RC, whenever you are struggling, if suppose you are really struggling with the waveforms, if you are really struggling with how to memorize the expression, just watch this lecture again and again, and what you will see, this particular portion will become very, very easy for you. Not only, and this is going to be the last lecture of this foundation course. Almost 6 lectures are there of 9 to 10 hour duration. So what I will recommend you, always watch this lecture before going to start power electronics. Then power electronics will become very easy for you. It will become very interesting subject for you. It will be among the favorite list of subjects of your, because you are not covering the fundamentals, because you are not clear with the fundamentals. That is the reason you are struggling in power electronics. Unless power electronics is most conceptual, most beautiful subject, interesting subject, and as per the application point of view are concerned, for an electrical engineer, this is very, very important. Whenever you want to convert power from one form to another form, and you want to have control on that conversion, you really need power electronics. So this is the purpose of this foundation series, to make you aware of the foundations of the power electronics, so that when you will really go into the chapters, you are going to rock there. So I hope this foundation series has served its purpose. Thank you for attending this session. Thank you for watching this video. Thank you.